Hey physicists, in this problem we're going to look at how much force is necessary to push a plate 2 meters on a side through the water at 5 meters per second. Hey, to set up this problem, let's take a look at what's happening with the water as it approaches the plate. When it comes to the plate, it can't go through the plate, so it gets turned around the plate. So we can see that we've had a certain amount of velocity, I'll call it in the x direction, and then it ends up stopping. It's eventually going to kind of flow around the plate this way. It'll end up having some y momentum, but really we take that force in the x direction to change the momentum of the water moving in the x direction. Let's see if we can take a look at some way of figuring this out. Okay, so I know it takes a certain force times time to change the momentum of something. Hey, what are we changing the momentum of? This water that's flowing toward the panel. And how much water are we changing here? Hey, we can imagine that flowing toward that panel. Each second we have a volume of water here that has a certain area and a certain length. Let's see what we know about this. Hey, we know that the mass of this water is equal to the volume of the water times its density. Let's try to kind of break this down a little bit more. The volume is going to be equal to that area on this plate times the length. Let's flesh this out a bit more. Okay, that's going to be the area times the velocity that we're traveling times some time. Hey, so for clarity, what I've done is when I'm talking about volume, I've added OL. So VOL is volume, and then velocity, I put a little tail on the V. Hopefully that helps. Hey, we know that our change in momentum is going to be equal to the change of the product mass times velocity. So let's see if we know what our mass is. Our mass is going to be our density times the area times velocity times the amount of time, because this will end up giving us our length of our rectangular solid. How about our change of velocity? Well, we're going from some velocity, let me put that little curly Q on there, from some velocity towards the plate, and we're going to be stopping motion in the x direction. Okay, so our change of velocity will really just be our velocity that we're moving toward the plate. Let's see if we can put this all together now. Hey, I know that Ft is equal to delta P, which is rho A V times T times V. The question here, we're looking at how much force is required. Let's divide each side by time. And I get this value. I get the force required to push this plate 2 meters on a side is equal to the density of water, in combined terms, times the area of that plate, times velocity squared, and look at our time cancels in both cases here. So that's our, that's the force required. I'm going to add another term in here. I've gone from the idea that the velocity of the water is toward the plate and then not moving toward the plate at all, but along the plate. That's an interesting idea referred to as the coefficient of drag. So I'm going to multiply this by this value C. When we go from a value of V toward the plate to not moving the plate at 0, we're going to call this value of C equal to 1. We'll see what that means a little bit later. Let's go ahead and solve our problem. Our density of water, 1,000 kilograms per meter cubed. The area, 2 meters by 2 meters, that's going to be 4 meters squared. The velocity we're trying to drag this through the water at is 5 meters per second. We're going to square that. And then we've given this value C when we end up having a velocity toward our object, and then we end up having 0 velocity. Think of the clay ball sticking against the door. We're going to give that a value of 1. I multiply this all out. and I get 100,000. We put all the units together, we find out that we have newtons. Hey, just a note about this value of C. You can imagine that, remember, if we're thinking about balls of clay that stick against a plate as being a value of 1, if we end up bouncing off and we return with the same value, we know that the velocity changes twice as much. What would be an example of that? Hey, so if I had something like, I was trying to drag a parachute through the water has to get in there, turn back around before it comes out. That would be an example of a high coefficient of drag. Would be something a little bit lower. Maybe if I have a nice airfoil, some type of a shape like that. As air or water passes around it, hey, it hardly changes its motion at all. We have values that are much, much less than 1 in a circumstance like this.